this video, we're going to talk about how to measure the arc length of a curve. So suppose you have that curve and you want to measure say just this little piece. Now I'm going to blow up that little piece, but understand it's very, very, very small. For all practical purposes, it's a straight line. And like I said, I'm going to blow it up. This is delta y, this is delta x, this is delta L, L for length. And what we have is that delta L is equal to delta x squared plus delta y squared square root. Pythagoras would tell you that. Now, what I'm going to do is I'm going to divide in the denominator inside the square root by delta x squared. So basically, underneath that radical, I multiplied by 1 over x delta squared. Okay, so I need to counter that by multiplying by the square root of delta x squared. But that's just delta x. And then what we get is the square root of 1 plus delta y over delta x, all underneath the square root sign squared, times delta x. And although I remember the formula, I can derive it this way. If I go for the whole length, I'm going to add up a lot of L's. So it's going to become the integral of 1 plus, now delta y over delta x, that becomes f prime of x, and it does say that I have to square it, take the square root of the whole thing, and then the delta x in the limit becomes dx. And this here is the length of an arc for a whole curve. So arc length of a curve. So we have the formula. We derived it, so anytime you forget it, it's not a big deal. You know how to get it. So now, suppose that you come to learn that f of x is equal to x cubed over 6 plus 1 over 2x. Now, you want to take the derivative of this. So it's probably friendly to rewrite this as x to the negative 1 over 2, at least the second fraction. Now, when you take the derivative, you bring down this 3x squared over 6 minus 1x to the negative 2. The 2 stays there. And then you get x squared over 2, because 3 goes into 6 2 times, minus the 1/2 times that in the numerator. But if I put it in the denominator, it becomes that. And this is factoring out the 1/2. This is 1/2 x squared minus 1 over x squared. And then you have to square this. Well, you have to square the 1/2, and you have to square what's in the bracket. Well, it's a subtraction. So you get the first term squared, which is x to the 4th, minus 2 times the product. The product is just 1, plus you get the second term squared, x to the 4th. Okay, but that's not enough. We want 1 plus f prime of x quantity squared. So we'll think of the 1 as 4 over 4 plus the x to the 4th minus 2 plus 1 over x to the 4th. Okay, now if I add that numerator, I get x to the 4th plus 2. 4 minus 2, or 4 plus or negative 2, that's positive 2. And we still have the plus 1 over x to the 4th. Now, what's in that bracket just happens to be x squared plus 1 over x squared squared. And it's over 2 squared. That is, it's x squared plus 1 over x squared all over 2 all squared. That is what this is. Now, I should have included one other thing in the problem. We want to find the arc lengths from 1/2 to 2. Okay, so the formula is straightforward. We'll call it big L instead of little l. It's the integral of. Now remember, that there is 1 plus f prime of x quantity squared. Okay, that's that. But now the formula is the square root of that. So we have x squared plus 1 over x squared all over 2 all squared dx, and dx is going from 1/2 to 2. Now, regardless of what you may think, the square root of x squared is not x. X is what you put in. It is not that. I mean, maybe when you plug in 4, 4 squared is 16, and the square root of 16 is 4. You plugged in 4, you got 4 back. But what if we plug in, say, negative 3? Negative 3 squared is 9, and the square root of 9 is 3. The problem is here, we didn't get back what we plugged in. We plugged in for x negative 3, and we got back 3. Well, let's see. We plug in a positive number, and we get that number back. We plug in a negative number, and we get negative that number back. Because negative 3 is 3. Ah, that's the square root function. This is, absolute value function. Okay, the square root of x squared is the absolute value of x. Now, if it turns out what's in the brackets is positive, then you get x. And for the record, if you have something more complicated, like, I don't know, x squared minus 3 squared, this will be the absolute value of x squared minus 3. Okay. So let us get rid of this, and let's see what's going on. Now, the first thing I would say is that the 2 squared in the bottom, 2 is positive, we square it, we get 4, take the square root, we get 2. We can definitely factor out the 1/4. And we still have the integral of 1/2 to 2, and for right now, it's x squared plus 1 over x squared absolute value. Now, x, these are x values. X are going from 1/2 to 2. Let me just look at the x squared function. Between a half and 2, it's always positive. And 1 is always positive, and we just argued that x squared is always positive. So this is always positive on our region from 1/2 to 2. And this is always positive from 1/2 to 2. So we can remove the absolute value bars. So x goes from 1/2 to 2 of just x squared plus 1 over x squared. And in anticipation of integrating this, I would write this as x squared plus x to the negative 2 from 1/2 to 2 of course dx. So you have the quarter. Integral of x cubed, x squared is x cubed over 3 plus you add 1 to that power, you get -1, and then you divide by that number from 1/2 to 2, and this is 1/4 x cubed over 3. Now this is going to become minus 1 over x. A 1 over a -1, that gives me the -1, and the x to the -1 that should be in the numerator, I put it in the denominator, made the exponent +1 from 1/2 to 2. The 1/4 comes in front. First I plug in 2. You get 2 cubed over 3 minus 1 over 2. Minus, you plug in the half. Half cubed over 3 minus 1 over our half. And now it's just arithmetic. The 1/4 in the front, 2 cubed is 8 over 3 minus a half minus 1/2 cubed is 1/8 over 3 minus 1 over or half. We'll clean that up in this step coming up. Now, before I dare subtract the 8/3 and a half, let's make sure nothing cancels out or we don't get whole numbers. For example, if in here, if somewhere in here, it said take away, add 5/3. Well, if you have 8/3 and you take away 5/3, that gives you 3/3, which is 1. So why would I spend time trying to combine 8/3 and a half? Okay, so we have 8/3 minus 1/2 minus. If I multiply that by 8, I get 1. If I multiply the denominator by 8, I get 24. If I multiply the bottom by 2, I get 1, which I won't even write. If I multiply the top by 2, I get 2. Okay, looks like I'm stuck getting a 24 in the denominator, which I will factor out. So you'll have 24 times 4. 8/3, I will multiply top and bottom by 8, because that's what it takes for me to get a 24 in the bottom. 3 times 8. On the other fraction, the minus a half, the minus half, I'm going to multiply by 12 over 12, and the 1 over 24 is fine. I'm going to multiply the bottom by 24 and the top by 24. If you want to see a 1 on the bottom, fine. 2 is the same as 2 over 1. In either case, I get 64 over 24. I factored out the 24. Minus 1 over 24. Minus 1 over 24, but I factored out the 1, minus 48 over 24. Okay, so I have 1 over 96. This here is 63. And I am taking away negative 47, which basically means I am adding 47. If I'm doing my math right, that gives me 110. 1 times 110 is 110 over 96. 2 goes into the top 55 times. 2 goes into the bottom, I guess, 48 times. Minus some silly error. That is how long the curve is. What curve, you may ask? I really don't know what f of x equals x cubed over 6 plus 1 over 2x looks like. But for argument's sake, definitely from 1/2 to 2, let her say that it looks like that. Well, we just found out how long that curve is. It's a little bit more than, it's 1 7/48 units, depending upon what the units are. Maybe they were inches, maybe they were feet, who knows? They could have been miles. Let us try the next problem. Suppose you have that y is equal to x to the 3/2 minus 1, and you want to find the arc lengths from 0 to 4. So we know the formula. You have to figure out what 1 plus the derivative squared is. So, first I would find the derivative. It's 3/2 x to the 1/2. Okay, that's the derivative. So now we want to know what 1 plus the derivative squared is. Well, there's the 1, and this here is the derivative squared. So we have 1 plus 3 squared over 2 squared, and the square root of x squared is just x. So we would write this with a common denominator. Okay. And if you like, we can denote that we're taking the square root of this. And what we can say is that that is the square root of 4 plus 9x all over 2. Okay, so we did not get something squared inside here, which is the same as this. That's not a perfect square. Now, we know the formula for the arc lengths is the integral from 0 to 4, in this case 0 to 4, of 1 plus the square root of 1 plus the derivative squared. But the square root of 1 plus the derivative squared turned out to be that. It's the square root of 4 plus 9x over 2. Well, first thing I'll do is pull out that 2, dx, excuse me. So it's the square root of 4 plus 9x dx. I'm going to call u, I'm going to let u be what is underneath the square root sign. So then du will just be 9 dx. Okay, so this here is going to become the square root of u. Okay, so I have that in the u world. But what about 9 dx? Sorry, what about dx? Well, if I had 9dx, I know what to call it. So what you can do is you can put a 9 in the numerator as long as you put a 9 in front in the denominator. 2 times 9 is 18. So we have the integral of 1 over 18, and then we have this u. And another way, we have the square root of u, which I can write that way. And then 9dx, oh, look at how nice. 9dx is du. So it's a routine integral. You add 1 to the power, and then you divide by 3 over 2. And you get, well, 2 goes into 18 9 times, and then 9 times 3 is 27. Now, you have two options. You can convert back to x's and then plug in the x units, or you can change the limits to u limits. Now you know that u is 4 plus 9x. Well, if x is 0, like the lower limit is, that means that u would be 4, because 9 times 0 is 0, and 4 plus 0 is 4. Okay, so the lower limit becomes 4. That's the u limit lower. Now, the upper limit for x is 4. Well, if x is 4, then u is going to be 4 plus 9 times x. It's going to be 4 plus 36, 40. So the upper limit is going to change from x equals 4 to u equals to 40. So over there, I plug in the upper limit. So it's just going from 4 to 40. The over 27 can stay. We have 40 to the 3 halves minus 4 to the 3 halves. Now, 40 is 4 times 10. So it's going to be 4 to the 3 halves times 10 to the 3 halves minus 4 to the 3 halves, of course, times 1 over 27. So in these two terms, I have something in common. 4 to the 3 halves. So and I factor it out. So what's left over is this, over 27. Now, how much is 4 to the 3 halves? To do such a problem, you have to know what questions to ask yourself. What times itself that number of times gives you that number? That is, what times itself 2 times gives you 4? Well, I hope you know that's 2. And then multiply that answer by itself 3 times. So that's 8. So we have 8 over 27. And now, can we really clean up 10 to the 3 halves? I would leave it like that, but just for the record, you can, because what times itself 2 times gives you 10? The answer is the square root of 10. And then we have to cube it. That is, we have to multiply the square root of 10 3 times. And I only know one thing about the square root of 10. Well, there's one thing for sure about the square root of 10. It's that special number that when you multiply it by itself gives you 10. That's pretty much the definition of square root of 10. It's the special number that when you multiply it by itself gives you 10. Oh, how convenient. I'm multiplying it by itself. So I'm going to get 10. Let's not forget to multiply it by the next radical 10. So you can write this, or you can write 8 times 10 to the 3 halves is that 10 square root of 10 minus 1 all over 27. I'd be surprised if a teacher really pushed for the bottom answer, but they're both nice answers. Okay, so that is that arc length. Now, let us try a couple of more problems. Suppose you come to know that y minus 1 cubed is equal to x squared. Now, keep in mind that the arc length is the integral of 1 plus, I'll use this notation, 1 plus dy dx squared, square root dx, but it also equals, thing is these limits will be different. It also equals the integral, say, from c to d of 1 plus dx over dy squared times dy. So the question is it easier to solve for x or is it easier to solve for y in this case? Now, to solve for x, all I need to do is divide by 2 on both sides in the power, and I have x, because 2 over 2 is 1. Now, I can do a similar thing for y. You have y minus 1 cubed is equal to x squared. Well, I can take the cube root of both sides. The only thing is that there's one extra step here. I need to bring the 1 over. I need to bring the 1 over. And I'm told that it's not 0 to infinity, excuse me. But I want the arc length from 0 to 8. It is understood that that's x and y. Those are x values, I apologize. From x equals 0 to x equals 8. Well, in that case, I know a and b. I know what I'm going from. I'm going from x equals 0 to x equals 8. Problem is that if I have y, then I don't know. Okay, then I don't know what it's going from. Okay, so it's probably easier to integrate this one. It was that one extra step bringing the 1 over, but then I don't have to go and find the upper and the lower limit. But basically what I would have to do is x is 0. So y minus 1 to the 3 halves is 0. So then y minus 1 must be 0, because only 0 to the 3 halves give us 0. And then y would equal 1. Okay, so x equals 0, y is 1. Now if x is equal to 8, now here we kind of luck out. Oops, x minus y to the 3 halves is equal to 8. Well, that means x minus 1 is 8 to the 2/3. And what I mean by lucked out is that I actually know what that is. What times itself 3 times give us 8? 2. Now square the 2. So that's 4. And then y is 5. So if I integrated with respect to y, instead of the limits being 0 to 8, they're going to be from 1 to 5. And I feel that was a lot of work. That was a lot of work. Sometimes you may not be able to get y equals. Sometimes you may not be able to solve for y. If you had y plus y squared, or y to the 2/3 equals x plus 3 over x, well, let's not do that. Let's just leave it at this. Good luck solving for y. Okay, so sometimes you can't solve for y. Then you're going to have to use this equation and find the y limits. But as I said, we're not going to do that here. It's too complicated. Or it's not too complicated. It's just not worth the effort. Alright. So we have that. Taking the cube root of both sides, x is y minus 1 is x to the 2/3. So y is equal to x to the 2/3 plus 1. So then y prime would be 2/3 x to the negative third, which is 2 over 3x to the third, and 1 plus y prime squared. Well, there's the 1. I'll square the y prime, and I'll get 2 squared over 3 squared times x to the 1/3 squared, which is x to the 2/3. Okay. And then I will get a common denominator. 9x to the 2/3. So 1 will become 9x to the 2/3 over 9x to the 2/3. Well, that's 1. Plus 4 over 9x to the 2/3, which is this. Now, the big problem here is that that doesn't look very friendly at all. That doesn't look friendly at all. Okay, let us look at this a little bit more. Here. Okay, fine, that is what it is. And if we happen to take the square root, we have to take the square root of all three of these. So we get the square root of the numerator. Now, the square root of 9 I know is 3. Now, x to the 2/3 is x to the third, which could be negative, squared. Okay, and then when I take the square root of this, I'm going to get x to the third, but absolute value. Okay, the nice thing is x is never negative. That's the only time a cube root is negative. So this is just x to the third. So 3x to the third. And we get that the length is the integral from 0 to 8 of this mess, which ultimately equals that. 9x to the 2/3 plus 4 under the radical. I'm going to bring that 3 out, and I have x to the 1/3 in the denominator, and the power should be in the upper corner, not below the base, dx. Okay. So I am going to let u equal to what's under the radical. So then du will be, well, you multiply 2/3 times 9 and you get 6. 6x to the negative 1/3 dx. But that is 6 dx over x to the third. Well, you know what? I have the dx over x to the third. Let me bring in a 6 in the top, and let me put a 6 in the denominator. Looks like this is going to work. So we have 1 over 18. 6 times 3 is 18. The integral, what's under the square root sign, as clear as day, I'm calling it u. But I'll take the square root of it, which is the same as u to the half. And what's being multiplied by that square root stuff is 6x over x to the third. But that's du. Pretty simple. So I have 1 over 18 u to the 3/2. Then I divide by 3 over 2. 2 goes into 18 9 times. So I have over 27 u to the 3/2. This time I'll substitute back. And u happens to be 9x to the 2/3 plus 4. And this was raised to the 3/2 from 0 to 8. Well, the 27 stays. Now, when I plug in 8, I get 9 times 8 to the 2/3 plus 4 all to the 2/3 minus, then I plug in 0. Well, I hope you see that's going to be 0. So 0 plus 4 is 4. I get 4 to the 3/2. Okay. Now, 8 to the 2/3 is 4. We already did that. What times itself 3 times give us 8? 2. 2 squared, 4. So that's 4 plus the other 4. And all of this gets raised to the 2/3 minus. How much is 4 to the 3/2? I claim it's 8. What times itself 2 times gives us 4? 2. Cube that answer. You get 8. All over 27. 36 plus 4 is 40. Let me get rid of this side work. It's really in the way. So now I have 40 to the 2/3 minus 8 over 27. Well, are there any factors of 40 that we know the cube root of? The answer is yes, it's 5. 840 is 5 times 8. So it's 5 to the 2/3 times 8 to the 2/3 minus 8 over 27. 5 to the 2/3, I can't really do anything to that. But 8 to the 2/3, that's 4. What times itself 3 times gives us 8? 2. Square the 2. You get 4. Minus 8 over 27. I'll do one last thing. 5 to the 2/3 is 5 squared to the 1/3, which is 25, the cube root of 25. So I'll write the 4 first, and then we have the cube root of 25 minus 8 over 27. My goodness, this problem's never going to end. I can pull out a 4. So I have 4 times the cube root of 25 minus 4 times 2. All over 27. That is the arc length. It's unusual that it didn't turn out to be it being, let's see if I can find it, it being 1 plus y prime square. It was unusual that it wasn't a perfect square, but it worked out nicely. Okay, now, a lot of people, I know of at least one professor who says that, no, a line is not a function, so you can't use this method to find the length of a line. Well, excuse me, a line is a function. So, suppose you have 2 points, x1, y1, and x2, y2. And let's assume that x1 is bigger than x2. One of these has to be bigger, so let's assume that it's x1. So basically, what's going on is this. There's a line that contains, so you're starting off with a line that contains those 2 points. Okay, you have a line that contains those 2 points, x1, y1, x2, y2, and I guess x2 is bigger than x1. Now, what we want to do is find the the length of that curve, better known as the distance between those 2 points. Now, of course, we could apply the distance formula, but I want to show that you're going to get the same exact thing when you use the integral method. Now, f prime of x, in this case, is going to be the slope of the line. I mean, after all, if f of x is mx plus b, then the derivative is just m, the slope. Well, I know the slope of that line. It's y2 minus y1 over x2 minus x1. Okay, so that's the slope. And if we happen to square the slope, well, we happen to square the slope. But that's not enough. I want to know what 1 plus that is. I want to know what 1 plus this mess is. How much is 1 plus it? Okay, well, let's see what we're really adding the 1 to. It's going to be y2 minus y1 squared over x2 minus x1 squared. And the common denominator is going to be x2 minus x1 squared. And I'm going to write that as x squared minus x2 minus x1 squared over x2 minus x1 squared plus this fraction, which is y2 minus y1 squared over x2 minus x1 squared. Now, okay, so let me just take the square root. So we want the square root of this mess. Now, what's underneath that square root sign is a constant. There's no x's, there's no y's. Remember, this is like 3, 5. And this is like 1, 2. Those are points. x1 and y1 and x2 and y2 are not variables, they're constants. Okay, so when I invoke the integral formula, the arc length is the integral, well, we're going from x1 to x2 times this constant, x2 minus x1 squared plus y2 minus y1 squared all over x2 minus x1 squared dx. That is the formula, because this here, all of this is the square root of 1 plus the derivative squared. Now, couple of comments. This is equal to the integral from x1 to x2. The square root of the top I'm not going to touch. But the square root of the bottom, well, that would be the absolute value of x2 minus x1. But I picked x2 to be larger than x1. That is, x2 minus x1 is positive. And the absolute value of x2 minus x1, if it's positive, is just x2 minus x1 dx. And now the magic happens. Like I said, this is just a constant. The square root of x2 minus x1 squared plus y2 minus y1 squared over x2 minus x1. Well, the integral of any constant dx is just kx. So it's just the constant times x. And x goes from x1 to x2. Okay, so we keep the constant the same. That is, I'm just going to bracket that off. First, I'm going to calculate what's in blue and then multiply it by the constant. Or multiply the constant by what's in the blue. Come on, green. Good, green. Squared plus y2 minus y1 squared all over x2 minus x1. And all of this gets multiplied by that. Well, first you plug in x2 for x minus, then you plug in x1 for x, and we are done. This cancels out. And then what we get is the square root. We just get the numerator. But now, if you know what's going on, you should say, wow, that's the distance formula. This is the distance formula between x1, y1, between that point and that point. I mean, isn't the distance formula, you subtract the y, well, let's do the x's first. You subtract the x's and you square it, and then you subtract the y's, and then you square it, and then you take the square root. That's exactly what we got. The only real difference is we called it L for length, because we are talking about the length of a curve. But the length of a line, well, this length happens to be the distance between those 2 points. Why? Because the shortest distance between 2 points is a straight line. If we wanted to talk about the distance between those 2 points, we would talk about that. And we would not talk about the length of the curve. They're different. But when you have a straight line, the length of the curve between x1 and x2 is the distance between those 2 points. So that is why in this case, the length, come on, scroll down. Okay. In this case, the length is equal to the distance. So we actually derived the distance formula using the arc length formula for integrals, which is pretty neat. Personally, something's a little bit wrong here, just a silly typo. This should be x1. Not a mathematician because I don't have a PhD in math, but as a math person, I think it's better to show the proof at the lowest level it can be shown at. And there's no reason to really use integrals to find the distance between 2 points. Okay, but you can. And remember, the distance between 2 points, that's the length of that line. Oh, length. I can use integration. That is why it works. That completes this video entitled Arc Lengths.